Earlier in the course, we considered how enthalpy was a function of temperature and how it might change with temperature. And you may recall that we wrote down an equation. I'm going to write this for a molar entropy. That if we wanted the molar entropy at some temperature T, that it would be related to the molar enthalpy, I should say enthalpy, not entropy, at some initial temperature T0 by the integral from T0 to T of the heat capacity at constant pressure dt. All right, this is just something we could get by directly integrating the total differential for enthalpy. So the question is, can we use this to help us determine what the enthalpy change for a reaction might be at a different temperature? If we use tables to find the enthalpy change of a reaction, those tables are basically going to tell us what the enthalpy change is for that reaction if it happens at a temperature of 298 Kelvin. All right, does that mean that these are the only temperatures that we can determine reaction enthalpies for? Well, I think obviously I wouldn't be saying this if that were true. So what I want you to do is consider our sample chemical equation for A plus B goes to C plus D. So it'll look something like this. And I'm including the stoichiometric coefficients because those are going to play a role since the enthalpy change is extensive. All right, now one way we can write down the enthalpy change for this reaction, under standard conditions, so this would be inherently at a temperature of 298 Kelvin, is it would be the sum over all the products of the stoichiometric coefficient times the enthalpy of formation, the heat of formation for those products, minus the sum over all the reactants. Well, let's use beta for this one to make it look different. So beta delta FH0 of beta. All right, so we're taking products of the heats of formation minus reactants of the heats formation. So we can get this number. All right, I don't think I need to convince you of that very much, but we can get that number. And so the question is, can I find the heat of reaction at another temperature T that is greater, say, than 298 Kelvin? I mean, I could have said less than, but I'll do greater than just because I think it will probably make better sense somehow. All right, so one way I can go about doing this is, what this implies is that all of these species are at that higher temperature. But what if I just wanted to take some sample of A and simply raise it from 298 Kelvin to A at some higher temperature T? Well, I know that the delta H for this reaction now is simply going to be given by this formula, where A is the subject of this formula. So the heat capacity in this case is going to be the heat capacity of substance A. So in other words, I can write this as simply the integral from 298 to the final temperature T of the heat capacity of substance A, which is in general itself a function of temperature dt. So I'll need to compute this integral unless the heat capacity somehow is magically a constant over this temperature range. But I'll need to do this for A, and I'll have to do it for B, C, and D also. So I'll just say also I'll have delta H of B, delta H of C, and delta H of D computed in a very similar way, where I'm just going to do an integral over the heat capacity dt from this low temperature to the final temperature T. All right, now how will I use that to get the enthalpy change for the reaction at that higher temperature? Well, let's draw a diagram. My diagram is going to have as its vertical coordinate enthalpy. Okay, that makes the most sense. And I'm going to have down here as my lowest point here, I'm going to have my products, C and D, at T equals 298. All right, now let's say that somewhere up in here, I'll put it, say, right here, I have a position of enthalpy that represents A and B, my reactants, also at a temperature of 298. So what this means now is that the standard enthalpy change for the reaction is going to simply be this amount. So this is delta R H0, and I'm putting the 0 there to indicate that this is at temperature of 298. So everything so far I've drawn here is for a temperature at 298. All right, so how would I have to change this in order to look at a higher temperature? Well, let's first look at simply raising the temperature of A and B. So let's say that raising temperature of A, this is delta HA, and that'll get me part of the way up, and then I'll raise the temperature B, so this will be delta HB, and that'll get me up to a point up here. Now I'm going to draw this all the way across because I want to reference it to what's down below here. All right, so in essence what I have here at this top point is A and B at temperature T. All right, that's this top line here. All right, now what if I do the same for C and D? Down here I've got C and D at a temperature of 298, so now I'll raise them each by some amount. So here's raising C's temperature, and then here is raising D's temperature. So that'll get me to a point here where I'll have C and D at temperature T, and this is delta HD. Okay, now I want to point out something I've done here. I have purposely made these arrows down here bigger than these arrows here, implying that the heat capacity of the products is greater somehow than the heat capacity of the reactants. Doesn't always have to be that way. I've chosen that arbitrarily, but what I want to emphasize here is that the heat capacities are different. So now when I look at the change from A plus B at temperature T to C plus D at temperature T, I'm looking at this change, and this would be the heat of reaction at temperature T. All right, so I've drawn all of this not only to make a great artistic statement, but also to emphasize that these two changes of enthalpy for these reactions do not have to be equal, and in fact in most cases will not be exactly equal. They may not differ by as much as I've drawn here, but they generally won't be equal. All right, but what we've done is we've basically given us a way that we can use these intermediate enthalpy changes that basically result from just heating up these different reaction species. We've shown a way that we can connect them to our reaction enthalpy changes. How does this work? Well, let me label the left-hand side 1 and the right-hand side 2. And what I want to do is I want to find what is the total enthalpy difference between between the bottom and the top in both cases. So if I do this for the left-hand side, what am I doing? I'm adding this enthalpy change from here to here, but that's going to be the negative of this heat of reaction. So because I'm pointing downward here, I need to take the negative of that. So negative of delta H of reaction, and this is at temperature of 298. All right, now to that I will add delta HA and delta HB, and that will achieve the level up here at the top. Now if I do the same thing for the right hand side, so that's number 2, I'll have delta HC plus delta HD, and then again I have to subtract the heat of the reaction because it's pointing downward. So negative delta reaction for this reaction at temperature T. So notice I've labeled this one 298, this one T. Now the difference here between these two lines is the same. So these two expressions are equal to one another. So if I set them equal to one another, and then I move this object to the other side of the equation, and I move these objects to the other side of the equation, what I'll end up with, and I hope you don't mind my having scrambled this around a little bit, but I wanted to make the math not be dominating this whole page, but I'll have the enthalpy change of the reaction at temperature T, that's this quantity that I've moved minus this enthalpy of reaction at the standard temperature, 298. And then on the other side, I'll have these two quantities, delta HC plus delta HD, minus delta HA minus delta HB. All right, so I basically have the products minus the reactants. But what are these delta H's? Well, they're just the thing that I've calculated up here. So in fact, I could write this whole thing, and this may not be something you would like to see, but I can write this whole thing as one big integral. It's the integral from 298 to t, and in this case, I've got the heat capacity of substance C plus the heat capacity of substance D. These are all at constant pressure. So I'll put those in parentheses, minus the heat capacity of substance A plus the heat capacity of substance B. And then all of this is dt. And these heat capacities are all implicitly functions of the temperature. So what I can see from this is that the change in the reaction enthalpy is really predicated on the differences in the heat capacities of the products and the reactants. Now, I've glossed over one particular important issue, and that is that I'm going to have to somehow also factor in the stoichiometric coefficients. So when I'm calculating this delta HA, theoretically I should also be multiplying this by this coefficient and doing this for each of those reaction species if I want all of the reaction to come out right. Now, I'm not going to do an extensive example here, but I will indicate that you can calculate, for example, that if I do this reaction, this is a simple reaction to synthesize water from oxygen and hydrogen. Now I'm making 2 waters out of this in the gas phase. If I do this at a temperature of about 300 Kelvin, I'll get a delta reaction, which is actually the heat of formation of gaseous water. That is minus 483.5. 0.6. All right, if I increase the temperature to 400 K and use the heat capacities for these different substances in that, what I'll end up with is a heat of reaction for this same reaction that is minus 485.6. And you'll see that these two are very similar to each other. They're very close, but they are different, and they are measurably different, as one could determine in a laboratory. So the heat capacity things, this is probably not the greatest example because the difference isn't that great, but the heat capacities do make a difference, and so when they are different between reactants and products, they will change the reaction enthalpy when you change the temperature.